Hi, everybody. Just want to go over some things for Unit 2. One big thing from Unit 2 is we're going to be using geometric shapes. We're going to be using those shapes to also predict polarity. And in doing that, discuss how our intermolecular forces are related to those polarities and also those shapes, right? Also, reminder, we'll be talking about S and P orbitals. And when we talk about S hybridization, we also include some of the D orbitals. Right? So one of the things we're going to look at is violation to the octet rule. Just a reminder, those are elements that are row 3, period 3 and on. Often you'll see that with silicon, phosphorus, your halogens, except for fluorine. Because remember, fluorine is in 2, so it cannot go beyond the octet. We'll come back to some stuff. Right? One of the things you also need to look at is as an ion, as an ionic compound, how will those models be arranged? Need to remember that they are arranged alternating. They're not layers. Also know that because of this diagram right here, bromine as a non-metal ion gains an electron, which causes the electron shell to get bigger. Lithium as an ion will become smaller. Also, lithium loses an energy level. And before we even do that, lithium starts out on period 2 and bromine starts out on period 4. Therefore, a big difference in size. So looking at that, we do need to draw a different kind of diagram than this. Also, the size of the ions will be different. Also, remember we deal with interstitial and substitutional. Substitutional where they have roughly the same state, same size particle, and interstitial where one particle size is a lot larger than the other. So we also have one of these problems on our test where we're looking at the percentage. So part of it is, do you draw it correctly according to the colors they're saying? Part of it is, do you have the right number of particles? And do you have them in the correct way? Is the size of the particles correct? Is interstitial versus substitutional? This diagram here is interstitial. We have a big particle and a little one. Substitutional, they'll be the same size. You do need to be careful with that. Right. So let me just go over you something I like to do. And we're gonna come back to this. Remember, I'll show you what we'll draw. We're going to draw. We're going to draw this, right? I'm going to show you how we started out. CO3 -2. Carbon is 4 valence. Oxygen is 6 valence. And there's 3 of those. That gives me 18 valence. 4 valence. -2 says I have 2 extra electrons. That's 24 I'm looking at. Carbon, oxygen, oxygen, oxygen. That took up 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So that's my maximum. But I still have a problem because carbon does not have an octet. So we'll take an electron pair away. and then multi-bond, carbon and oxygen. So everything has an octet now. Each oxygen now has 8. Each and the central carbon now has 8. Okay. Also remember, because there's an ion, we're going to put the brackets around it and the charge. This has a resonance structure because I could move that double bond there, or I could move that double bond here. Okay. So I have 3 different resonance structures for that substance. And let me clear that. Right. And that's what we have here, something similar. We also need to look at formal charge being okay. Which one of the possible compounds probably is going to exist? Okay. Couple things you look for. Right? One of those things you look for is the number of valence electrons. Right? You can subtract from that the non-bonded pairs plus 1/2 of the electrons involved in bonds around the atom. Okay. Oxygen valence electron 6, carbon valence electrons 4. So that doesn't change for either model. We'll start with a model on the far right. We see that for oxygen on the far right, we have 2 electrons that are non-bonding. So that's 2. We have 2, 4, 6 electrons involved in the bond. So half of that belongs to oxygen. So that's 3. 3 plus 2 gives us our 5. And then we look at that, that gives us a +1. Not really good because oxygen is the most electronegative element in the group. So it should have a negative charge or 0 if at best. And we do like when they're 0. And we look at carbon. Carbon has 4 bonds around it. So that's 4, that's 8 electrons. Half of 8 gives you 4. So that works out. The oxygen on the right still starts off with 6 valence. 2, 4, 6 electrons that are non-bonding. 1 bond. So that gives you half of the 2 electrons is 1. 6 plus 1 is 7. 6 subtract 7 gives you a -1. So in this case, we have oxygen has a -1, that's not bad. But the other oxygen has a +1. So not really good. The sample on the far left, we have oxygen having 6 valence, carbon having 6. I'm going to start on one of the far left. So this is the one I'm working on. So oxygen has 2, 4. That's 4 valence. Sorry, that's 4 electrons that are non-bonding. And 2 bonds. So that's 2 electrons. Then we have 4 plus 2 is 6. We're good. Oxygen has 4 valence. 1, 2, 3, 4 bonds. So that's 4 valence, 4 electrons that are non-bonded, but also has 0 non-bonding, but half of the number of electrons give you 4 electrons. So that's good. Carbon is 6 valence. 2, 4. That's 4 valence. I'm sorry. 4 non-bonded pairs, 4 non-bonded electrons. We have 2 bonds between carbon and oxygen. That gives you 2 electrons. 4 plus 2 is 6. So that's good. In this case, you'll notice that formal charges is 0, 0, 0. That is best. Okay. Sometimes you might have the charge of the oxygen because it's most electronegative being -1. That would be okay. But both of them would have to do something differently. Okay. So formal charges are not that bad once you get used to it. Another example, we want to work that out to consider which one is best. And in this case, going back to what I said before, Oxygen on the one on the far left is +1. That's no good because oxygen is very electronegative. But then you do have nitrogen um in there involved in that, but oxygen is more electronegative than nitrogen. So it should have the negative charge. Same thing with sample 2. Nitrogen has the negative, but oxygen is the most electronegative. Then we go to the third sample where oxygen has a -1 charge, and that would be the best one since it is the most electronegative. And you should work through this one to figure out, based on formal charges, which one is correct. You can't just say, oh, this is the one I've been using for many years. You have to prove which one is the most likely compound based on formal charge. So the sample, figure that one out. So this one was also on the test, right? One of the challenges with this one is you need to figure out how many dots should be there. So a lot of you did not figure that out. So I have hydrogen, carbon, oxygen, nitrogen. I have 5, 2, 2, 1. So in terms of valence, that's 5 valence, 6 valence, 4 valence, 1 valence, right? So let's see, 8, that's 10, 5 and 5 gives you 20 total. That's 20 and that's 30 valence electrons total, right? Every dash is a pair, 1, 2. Why do I do for hydrogen? Because hydrogen cannot bond to more than one thing. So right now I already used up 2, 4, 6, 8, 10. The only thing I have left now are 20, right? 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. Okay. I'm going to double check. Nitrogen has 8. Carbon has 8. Ooh, I do have a challenge. The second carbon has 6. So I cannot add more, so I will multi-bond. Multi-bond that carbon, okay? And now let me double check. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. And I'm good, okay? Get out of your valence electrons and make it work, or you're gonna mess yourself up, okay? Just remember that. Make it work based on your valence electrons. Now shape. So after we started practicing Lewis structures, we then need to say, okay, if I have these Lewis structures, I need to figure out what the shapes are, because these shapes dictate polarity. And when you get to college or organic chemistry, we'll talk about shape dictates function. Shape dictates function. So if the shape is different than another shape, it can't function the same way. You also know that a lot of things have a lock and key mechanism. If we could get a molecule to have the same shape as another key, it could then open up that floodgate, causing problems in the body. Okay. So we need to look at the Lewis geometry versus the Visper geometry versus the molecular shapes and the relation. You need to remember these primary geometry. Linear, trigonal planar is 3 zones, tetrahedral is 4 zones, Trigonal bipyramidal is 5 zones, and octahedral is 6 zones. Okay. And you must learn these. Okay. As I was saying, Lewis structure. Make your valence electrons work. Electron domain geometry or Vesper geometry. Make the shape look roughly like what it should look based on angles. And remember, your geometry is based on the number of zones around that central atom. Nitrogen has 4 zones. It's a tetrahedral. However, it has 1 non-bonded pair, makes it unbalanced. That unbalance makes ammonia, NH3, a polar substance. Okay, you have to remember that. That non-bonded pair pushes down on the bonds. See what the different geometries are. We see it's trigonal pyramidal. Okay. Also, look at what the lone pairs do. The lone pairs cause some changes. Those non-bonded pairs. Those non-bonded pairs cause some changes. We go from 109 to 107 to 104.5 as we add in, or as we get rid of another bond to just have a non-bonded pair. We do need to realize how that works. Trigonal bipyramidal is interesting when you're looking at it linear. Is the only one that can be linear, and trigonal bipyramidal are the only ones in this structure that can be non-polar. Right? Octahedral and square planar are the only ones in this structure that can be non-polar. Right? And if you look at it, remember, to be non-polar, all atoms attached to the central atom must be the same, and the non-bonded pairs must be balanced. So looking at this square planar, you see that the non-bonded pairs are on the opposite plane, making that acceptable. In this earlier model, you see that for this linear shape, the non-bonded pairs are on the other plane also. And this is based on the research that says how the atoms come off, leaving the non-bonded pairs. So another thing that pops up, electronegativity. One of the things that happened on the last test is I gave you electronegativity from the New York State regions. It messed you up. You weren't thinking. You kept looking for numbers. And because you weren't thinking, you didn't always get a good reason to write down or a good answer. So without looking at electronegativity values, which are bond is most polar, remember polar, we often say are the opposite ends. So you're looking for the substance that is furthest apart as your choice. So you have S and S, Si and Si, that will be nonpolar. Si and P next to each other. Si and S further apart, but Si and Cl even further apart. So that difference in electronegativity values will be greatest for the one that's furthest apart. So speaking of further apart, we have these models here. Okay? Looking at how close the electrons are, how close the atoms are to each other. And how does that work in terms of calm, in terms of releasing energy, and in terms of making it stable. Okay. We know that atoms become more stable when they lose electrons, okay? Because that gets rid of that jitter, that energy that we see, and it makes them naturally calmer. So when we start off on the far right, we see that they're far apart. As they move closer and closer together, getting more stable, and then they get to the point where they've released a good amount of energy and they're next to each other. Okay. So you also notice the distance between the particles that are now acceptable. Oh, distance between the particles. Right? And you'll see some models that have two lines. And I'll ask you which one is more stable, be the one that is furthest to the left, to the y-axis. So if we could predict that the PE is lowest, that is the most stable. So hybrid orbitals, all right. So the big thing with this is just counting. A single, double, or triple bond means the same thing to us because we're looking at zones. Okay, non-bonded pair is a zone. Single bond zone, triple bond zone, double bond is zone. So every zone is what we're looking for. If we have 4 zones, that's this one. If we have 5 zones, 6 zones. Non-bonded pairs and bonds. So bond order also comes up. So just remember bond order. The easy model is 3 is better than 2, 2 is better than 1, but that was a simple method. You also have to look at, let's look at the number of non-bonding electrons, the number of anti-bonding electrons, divide by 2. Okay? And for most of you, when you did the calculation, you did a good job. So you're looking at how many. So sometimes you get a 1.33, and that's better than 1. Right? We also need to look at which kind of bond is strongest. So triple bond is strongest because you have 6 electrons being shared, pulls it closer together. Our single bond is the weakest because you have only 1 pair of electrons being shared, so that bond is the longest. And it's just something you need to get used to. If I attach 2 fingers versus 1, I can hold on, pulling on my fingers a lot more, 3. But when I just have 1, it easily slides off versus the others. I think that's it. Um, if I didn't cover something, let me know. And then I'll just make another video for that. All right. But make sure you study. Make sure you study. Get those shapes down pat, and also make sure you um understand your Lewis structures. Oh, did forget polarity. Polarity is bigger in unit 3 than unit 2, but you do need to look at that. If I have a non-bonded pair, it's most likely gonna be polar, with an exception being square planar, which square planar that is not going to be polar. That's gonna be non-polar if all atoms are the same. And linear when it comes to trigonal bipyramidal, which is 5 zones, then that's gonna be non-polar also. All right. So let me know if anything else needs to be done, and then I'll throw a video together. You have a good one.